what the barriers are there to building scalable quantum computers?
Well, there's definitely a large number of barriers. Hardware is the foremost one, and there's a lot of challenges associated with hardware. And John and Chris are really the experts here. I think one thing that's happened in recent years, to me, it seemed it happened around 2015 or 2016, is that the emphasis went from making progressively better qubits to starting to scale up systems. I guess this is around the time that IonQ was founded. So Chris may have some views on this and why quantum hardware looked good to him at that time. But there was definitely a period where the quality of quantum gates in a lot of systems, um, the fidelity of entangling gates, which is basically how well you can entangle two qubits, how good you can do a gate between two quantum bits without an error occurring. That has come down a lot since the early days of quantum computing. It was initially high, and the error rates are now coming down where they're less than 1%, coming down to maybe less than 1/10 of 1%, which is, really an extraordinary achievement. But it seems to me that this has brought around a emphasis towards getting to larger scale systems. And you have some problems with making individual qubits well behaved. But as you start to scale up, there's all sorts of engineering problems that are involved as well. And I guess I will leave it up to John and Chris to talk more about that. Over to you guys.
Yeah, so let's dive right into the kind of challenges that Chris and John, you've been facing in building a tech. Because as all of you have pointed out, there's a huge bunch of like barriers and things to be, like a lot of nuance, right? That needs to be done and detail to get right precision. So maybe back to Chris, what challenge are you facing in building your tech?
Yeah, good question. Again, I could speak for an hour on that. I think we're going to all say this at the intro to every one of our answers. In the technology I work with, again, I come from a kind of a qubit physics point of view in my early life. But 5 or 6 years ago, this timing that Joe mentioned, a few things happened. We noticed that that our system, I call it a system. Let me define for about a minute what that is. Our qubits are composed of individual atoms. These are charged atoms, they're ions, and they are electromagnetically confined with a bunch of electrodes. Think of a magnetically levitated train if you want, only these are atoms, and it's electric, not magnetic. But apart from that, the chip behind me, you can see, has about 100 electrodes, and we apply voltages to those electrodes, and the atoms float above that chip in a vacuum chamber. These atoms are affected, they're measured through laser beams, so it's a very big optical system. So what we realized 5 or 6 years ago was, and this will get to what the challenges are going forward, what we realized is instead of doing atomic physics, we're not really doing physics at all. Our systems are so well behaved, these are atoms. We're not going to learn anything more about the atom. We sort of know everything we need to. Atoms are perfectly replicable, there are no errors. When we make two atoms of the same isotope of the same element, there is no yield issue. Yield is exactly 100%. We have to make them, we have to control them. But it's really an optical engineering challenge going ahead. And what we noticed 5 or 6 years ago is in the morning, we would tune up the system. You have to aim laser beams, a lot of technology there. But in the afternoon, we were running algorithms. We were sitting at our computers, our regular computers, and running circuits right on our systems. We were very far removed from atomic physics. We weren't thinking about the qubits anymore. We were thinking about compiling the algorithm, making it work better, because there are errors in the gates. We can only run it so far. We wanted to make it more efficient to do some type of a task, some small algorithm to make some particular target quantum state. So we've been paying attention over the last 5 or 6 years at IonQ in particular on making the system more reliable, making it smaller, not to be cute, but when you make an optical system smaller, it performs better. And also we can we can talk about scaling. If you're going to scale it up, we really need to make it small and modular. We know exactly how our system will scale. Exactly. And what I mean by that is that we don't worry about any manufacturing issues. It's not about figuring out some fundamental physics of how a surface will interact with our individual atoms. That really doesn't exist. It's all about engineering control errors, making an optical system better. And so the reason IonQ formed 5 or 6 years ago is these are things that are very hard to do at a university. Universities are not very good at making commoditized devices that can be made standard. That's really what industry does. And so we felt there was a great need for an industry in our field of atomic qubits. So again, I don't mean to sound super general here, but the challenges are manyfold, but they're not physics. It's not the physics of the qubits. It's certainly not atomic physics. It's much more about engineering. And this is what gives us huge confidence going forward in our scaling. We don't know exactly all the technologies we'll bring in, but we sort of know what it will look like in the end. Integrated optics is a hint. Bringing optical systems right on the chip itself where the atoms are located. We don't really do much of that yet, but I think the whole community is moving in that direction. And so we're, I'm again, as an atomic physicist, I'm not an expert in integrated optics and integrating optical waveguides on silicon chips. This piece of silicon behind me coated with gold. So we're indeed going to leverage the fabrication community out there that has been put to use for so many solid-state qubit architectures, but we're going to use that to help us integrate optics to control our atomic system.
And John, do you face the same kind of challenges where it's more engineering rather than physics?
Yes, I mean, absolutely. I think the field in the hardware area has certainly moved in that direction. I always like to say it's been elevated to an engineering problem, though my colleagues in physics, kind of dismiss engineering problems as the point at which it's no longer relevant. But I think that's where it gets exciting. But of course, there's a whole set of different engineering problems. In a sense, a lot of what we what we think about, is trying to turn some proof of principle demonstrations that are performed, within silicon using very bespoke fabrication methods, for example, in university clean rooms, and trying to understand how we can create that kind of qubit functionality within advanced CMOS processes. So for example, a 2-qubit gate has been demonstrated in a silicon device fabricated in a university clean room now with over, I think it's over 99.5% fidelity, which is well above the fault tolerant threshold and comparable to superconducting qubits, if not Chris's nice ions. But that's that's a bespoke process. Is not the same kind of CMOS process performed on 300 millimeter wafers, which is used in industry, and it's very advanced. You can produce billions of devices, but there's a large rule book that tells you what you can and can't do. And so understanding how to get that kind of functionality within the within these kinds of more industrial processes is a major challenge. But it also opens up the opportunities, because if you're using exactly the same or similar processes that are used to make computer processors, well, then actually you can incorporate some of that technology on the same chip, and you can really integrate the control and readout electronics with the qubits in a way which is much more natural, should we say, than in other systems. But yeah, I sort of strongly echo the message from Chris that doing all of this, it's very difficult to see how it can be done using within a university environment, because you do need to pull together such different expertise, IC engineers, of course, quantum architecture theorists, but quantum engineers running measurements and optimizing. Everything else that you need, from the software control to bespoke circuits for the readout. So it's a very interdisciplinary engineering challenge, and a startup has been a fantastic environment in which to bring together that sort of team and make progress.